Let's talk about the way two lines can exist in a 2D plane. If we think about it, there's really only three possibilities. The first, of course, being that those two lines overlap each other. So something like that. The second one would be when those two lines intersect each other. And the third one would be when they neither overlap nor intersect each other. And so L2 and L1 end up being parallel to each other. Now let's talk about the shortest distance between these two lines. In the first case, that is overlapping, they are clearly hugging each other. So the distance is 0 throughout. However, in the second case, during intersection, when those lines touch each other, the distance would be 0. So the shortest distance is really 0. But in the third case, these lines never meet, so it is a non-zero value. The way to find it is take a point on L2 and draw a perpendicular line from L2 all the way to L1 that is also perpendicular to L1. And the length of that line would be D, which would be the shortest distance, and it would be the same throughout those two lines. Now, let's take these ideas to 3D space. Just like 2D, we will have overlapping, intersecting, and parallel lines in 3D. However, there will be another case in which two non-overlapping lines will neither intersect nor be parallel to each other. That means that even though they never meet, the distance between those two lines would keep changing. And since the distance is changing, there will be a shortest distance. Now, I agree, something like this is a little hard to visualize, so let me help you with that. Now, imagine a cube in 3D space, so something like that. And the corner of the cube would be at the origin. And these are the axes, with the red one being the x-axis, the green one being the y-axis, and the blue one being the z-axis. And so that's our cube. And let's pick a face. Let's pick this one right there, and let us add a line that is diagonal to that face, like that. And now, let's pick another face now. Pick the top one and add another diagonal. There. Now, as you can see, these two lines don't seem to intersect. But what happens when we extend them? Okay, so let's extend the yellow one by a factor of 10 and the purple one by a factor of 10 as well. And now, I know it's a little blurry now, so it's hard to see, but on zooming out, you'll see that these lines actually still never meet. And let's go back and shorten these lines again and try to look at it from a different way. Let's remove the cube and place our camera at a plane like that. Where the yellow line is perpendicular to our plane from which we're viewing the scene. So now, no matter how much you extend this yellow line, it would always be perpendicular to the plane. So it would look like a point. And of course, this point is never going to meet the purple line. So, so that's one way to visualize these lines that neither intersect nor are parallel are called skew lines. As you can see, there is a lot of different line segments that you could draw to find the distance between these two lines. But how do we find the shortest distance? For that, we need to quickly recap the equation of a line in vector space that goes through a given point. Let's say that's represented by A, so let's draw the graph, and that's A, that's the position vector A, and is parallel to another vector, B. And that would be our B. And let's draw a pink line that's parallel to B passing through A. To find the equation, we'll take a point R on the line and let's have that position vector called R. And so the difference between R and A, you can see, would be a multiple of B. In this case, it's 3 times B. So we can say R minus A is lambda times B, or R is equal to A plus lambda B. And that is our equation of a line. Okay, so let's come back to finding the shortest distance between two skew lines. Let's give these lines equations for better representation. So let's say the yellow one, L1 is R is equal to A1 plus lambda B1. And the purple line, L2, is R is equal to A2 plus mu B2. Let's take a line segment that connects the 2 points represented by position vectors A1 and A2. So A1 would be on L1 right there, and A2 would be on L2 somewhere there. And let's add a line segment. So the orange line segment is joining A1 and A2. Our shortest distance, though, would be a projection of this line segment along the direction of a line that is perpendicular to both L1 and L2. So we have this pink line that is perpendicular to both L1 and L2. And when we take a projection of this orange line, so let's shorten it up, and the projection would look something like that. And this projection, let's call that P, would be our shortest distance between these two lines. In a sense, that would mean that our distance D would be the magnitude of the orange line segment. So O times cos theta, where theta is the angle between O and B. But from dot product, we can say that cos theta is equal to the dot product of O and P divided by the product of the magnitudes of O and P. That means, let's break this down first. So O is a line segment joining the two position vectors A1 and A2. So we can say that O is equal to A2 minus A1. Now P, like we said, is the shortest distance D in magnitude in the unit direction, let's call that N, of the line that's perpendicular to both L1 and L2. And now the magnitude of P is just D. And let's not change the magnitude of O. So then our cos theta is equal to D in the direction N times A2 minus A1 divided by D times the magnitude of O. And since we have D in both the numerator and the denominator, we can get rid of that to get cos theta is equal to A2 minus A1 in the direction of N over the magnitude of O. This means, so going back to what we had before, the D is equal to the magnitude of O times cos theta, we can say D is equal to A2 minus A1 in N direction. And let's just move that up. Now let's try to find N. We can find that vector by taking a simple cross product. The direction vector for L1, as we know from the equation of a line, is B1, and the direction vector for L2 is B2. Then the cross product of B1 and B2 would be equal to the magnitude of the cross product of B1 and B2 in the unit direction of the shortest distance vector, N. So then, N is equal to the cross product of B1 and B2 divided by the magnitude of the cross product of B1 and B2. So, replacing N from earlier, we can say D is equal to the magnitude of the dot product of A2 minus A1 and the cross product of B1 and B2 divided by the magnitude of the cross product of B1 and B2. And yep, there we go. That's our shortest distance.